Okay, hello and welcome back. In this video we are covering section 7.5 on the sum and difference formulas. So this is going to be the first in a few videos where we're going to be adding to our list of trigonometric identities and formulas, and this will be our first example of that. So let's take a look at what they mean by sum and difference formulas. The sum and difference part is referring to a sum or difference of angles. So we can see, we'll start with the cosine. They give us a formula for the cosine of, and they use alpha and beta, these Greek symbols for two angles. You could use A and B if you feel more comfortable doing that. Um, so we have a formula for the sum of two angles in the cosine. So cosine alpha plus beta, and that's equal to the cosine of the first angle times the cosine of the second angle. So cosine alpha cosine beta minus the sine of the first angle times the sine of the second angle. And then they give us a similar formula for the difference of two angles inside of a cosine. So cosine alpha minus beta. And the structure is the same, but notice the sign flips. So cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. So it's important to notice that for the angle addition formula for cosine, there's a subtraction involved. And for the difference for angle subtraction, alpha minus beta, there's a plus in the formula. So you get that swapping of signs. It might be tempting to put a plus with the plus and minus with minus, but it's flipped for the cosine. So let's practice using this. Let's see a couple examples of where this would become very useful. This will allow us to evaluate trigonometric functions for some angles beyond just our regular unit circle angles, if we can express them as the sum or difference of some unit circle angles that we've seen before. So let's look at this first example. We have the cosine of 75 degrees. And it's beyond 60 degrees, but less than 90 degrees, so it's not one of those sort of classic unit circle angles we've seen. But we can try to get it by combining some of them together. Like notice if we can express 75 degrees as 45 degrees plus 30 degrees. So we can call the 45 degree angle our first angle, alpha, and 30 degrees can be our second angle, meaning that we can express the cosine of 75 degrees as the cosine of 45 degrees plus 30 degrees. So let's use that first formula, and I'll write it out here just to reference. Cosine of addition of two angles, I'll say alpha plus beta, is cosine alpha cosine beta minus sine alpha sine beta. So let's express this in terms of our two angles that we have. So for us, the cosine of 45 plus 30 will be the cosine of 45 degrees times the cosine of 30 degrees minus the sine of 45 degrees times the sine of 30 degrees. So now we just need to evaluate each of these, plug it all in, and simplify our answer. So cosine of 45 is root 2 over 2. Cosine of 30 degrees is the square root of 3 over 2. Minus sine of 45 is also root 2 over 2. And the sine of 30 degrees is 1/2. So this will be the square root of 6. When you multiply two square roots, they multiply into each other. over 4 minus the square root of 2 over 4. So we can express this as a single fraction. There's different ways we can express this answer. We can say the square root of 6 minus the square root of 2 over 4, since they have a common denominator. We could also, alternatively, from this previous expression, factor out 1/4. Like we can write it as 1 over 4 times the square root of 6 minus the square root of 2. And I think that's how the textbook likes to show the answer. Let me just double check. Yeah, they end up factoring out the fraction in front, but it's either of these will be equivalent. So I kind of like this first one because it's a single fraction. So it's kind of an aesthetic choice at this point. But I'll write down what the textbook gives. All right, let's look at another example. So we'll reference these formulas, and really it's just plugging them in, plugging everything in and evaluating. So let's look at this next one. Now we have a radian angle. We have the cosine of pi over 12. So pi over 12 is not one of our core unit circle angles, so I'm going to try and express this as a sum or difference of two other angles. And this might take a little bit of guess and check, especially since we have this denominator of 12. So I can try using some numerators that will end up simplifying the denominator. Like I have pi, 1 pi in my numerator, and I know 3 and 2 both go into 12, so I can try expressing this as 3 pi over 12 minus 2 pi over 12. That will give me the 1 pi over 12. And 3 over 12, that simplifies to 1 over 4, so that becomes pi over 4. And 2 over 12, that simplifies to 1 over 6. So we can say pi over 12 is equivalent to pi over 4 minus pi over 6. And those are two angles we can pull from the unit circle very easily. So let's rewrite things. We're looking for the cosine of pi over 12. So that can be expressed as the cosine of pi over 4 minus pi over 6. So that'll be the cosine of the first angle times the cosine of the second angle. And since it was a minus, there'll be a plus here. That's how I remember. It'll flip. Then it's the sine of the first angle times the sine of the second angle, pi over 6. So once we have it all filled out, we just need to evaluate and simplify. So cosine of pi over 4, that's root 2 over 2. Cosine of pi over 6 is the square root of 3 over 2. Then plus sine of pi over 4 is root 2 over 2. Sine of pi over 6 is 1/2. So we're getting pretty much the same result as last time, except we have a plus instead of a minus. So this will become square root of 6 over 4 plus the square root of 2 over 4, which we can either write as a single fraction, root 6 plus root 2 over 4, or factor 1/4 out and write it as 1/4 times the square root of 6 plus the square root of 2. Either way. So for the cosine, angle addition or subtraction, so we could have the cosine of a plus b or the cosine of a minus b. It's cosine of the first angle times cosine of the second, and then whatever the operation was, you flip it. So if it was a plus, we get a minus in the formula. If it was a minus, we get a plus. and then it's the sine of the two angles multiplied together. So cosine, cosine, sine, sine, with a plus or minus in between. All right, let's see for the sine. We have some similar equations, but let's look at some of the key differences. So the sine of the sum of two angles, notice this time the sines and the cosines um, are paired together. So sine of the first angle, cosine of the second angle, those are multiplied, plus cosine of the first angle times sine of the second angle. So sine, cosine, cosine, sine. That's how I remember it in my head. And with the sine, if it's a plus, if it's angle addition, you do get a plus in the formula. And we have the same thing for subtraction, and notice there's a subtraction in the formula. So for sine, it's sine of first angle, cosine second angle multiplied, plus or minus cosine of the first angle, sine of the second angle. Sine, cosine, cosine, sine. So let's practice. Let's do a couple of examples. The first one, example 3, is asking for the sine of 7 pi over 12. So 7 pi over 12, we need to express this as the sum or difference of two known unit circle angles. So we can just kind of guess and check. I know 4 plus 3 is 7, so I can try 4 pi over 12 plus 3 pi over 12. So that would reduce to pi over 3 plus pi over 4. And those are good angles to use. So let's plug into our formula. That means we can write the sine of 7 pi over 12 as the sine of pi over 3 plus pi over 4. So this will be sine of the first angle times cosine of the second angle plus, because there's a plus here, plus the cosine of the first angle times the sine of the second angle. Now let's just plug in and evaluate. So sine of pi over 3 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Plus cosine of pi over 3 is 1/2. And the sine of pi over 4 is root 2 over 2. So we will get square root of 6 over 4 plus the square root of 2 over 4. So just like last time, we can write it as a single fraction or pull out the 1/4. So 1/4 times root 6 plus root 2. Yeah, we can't combine these two together even though they're both under square roots. We can't add them like terms. If they were multiplied, we can multiply them into each other. But it would have to be 2 root 6s or something for us to combine them together. All right, let's take a look at another. So now this is kind of working backwards. It's asking us to find the exact value of sine of 80 degrees times cosine 20 minus cosine of 80 degrees times sine of 20. And initially we might think, oh man, we're going to have to try to do some kind of angle addition or subtraction with each of these. But notice it's already in that formula. Sine, like sine A cosine B minus cosine A sine B. So that, and I'll write it out here, that was our formula for the sine of the difference of two angles, which you have here, sine A cosine B minus cosine A sine B. So that means if we have the sine of 80 times the cosine of 20 degrees minus the cosine of 80 times the sine of 20. We can write this as a single sine function of 80 degrees minus 20 degrees. And that's nice for us because 80 minus 20 is 60, so really this is just the sine of 60 degrees, which we do have from the unit circle. So sine of 60 degrees, that's like the sine of pi over 3, is the square root of 3 over 2. So sometimes you'll be presented this situation kind of backwards, where they give you this like expanded out formula, and you can condense it into a single expression, and that might be a nice unit circle angle to work with. Okay, let's look at a slightly more complicated example. So kind of a messy prompt here. So they say if sine of alpha is 4 over 5, and alpha is between pi over 2 and pi, so that's the second quadrant, and sine of beta, our second angle, is negative 2 over root 5, which is equal to 2 root 5 over 5 if we rationalize. And beta is between pi and 3 pi over 2, so that's the third quadrant. Find the exact value of each of the following. So let's just go through. They've given us some messy information here, but let's see how we can use it in order to answer these questions. So part A is asking for the cosine of alpha. And they give us the sine of alpha. Let's just start there. They say the sine of alpha is 4 over 5. And alpha is between pi over 2 and pi. So it's some triangle in the second quadrant. We can imagine something like this. That'll be our angle. And sine is opposite over hypotenuse, so we can write this as 4 and 5. And if you recall, there's that pattern of 3, 4, 5 triangles. We could also get this value if we call this x and solve via the Pythagorean theorem. But if you ever see a 4 and a 5 on a right triangle, the other side length has to be 3. So that's a Pythagorean triple, 3, 4, 5. But we should make this a negative 3 since we are in the second quadrant. If we imagine this is some point in the second quadrant, this would be negative on the x-axis and then positive on the y-axis. So that's something to keep in mind. The quadrant that they give you informs you on what should be positive or negative, and that can be a key difference between getting a question correct or incorrect. So now that we have this triangle, we can use it to find out what the cosine of this angle should be. Cosine is adjacent over hypotenuse, so it should be negative 3 over 5. All right, let's look at part B. B asks for the cosine of beta, so let's take a similar approach. They tell us the sine of beta is negative 2 over root 5. Let's use that version. And then they say that beta is between pi and 3 pi over 2. So it'll be in the third quadrant. That triangle will look like this. Let's call this our angle. So the sine of beta is negative 2 over root 5. And the sine is opposite over hypotenuse. So negative 2 here. And then we'll put the square root of 5 on the hypotenuse. And it makes sense that the 2 is negative because this will be below the x-axis over in quadrant 3. And we should have a negative direction here as well. So let's find this missing side length. You can't recognize the Pythagorean triple here, especially with the square root. So let's just use the Pythagorean theorem. Let's call this x. So I will say x squared plus negative 2 squared should equal the square root of 5 squared. So that gives us x squared, negative 2 squared is positive 4. And then the square root of 5 squared will just undo the square root. We'll just get 5 here. So if we subtract 4 over, we get that x squared equals positive 1. So take the square root of both sides and we get that x equals plus or minus 1. But since we are in the third quadrant, we're saying x, this distance here, should be negative. Both x and y should be negative. So let's take this negative version. Negative 1. So I'll fill that in here. Our missing side length. Now let's use this to solve for sine. Or for the cosine, rather. So I can say the cosine of beta is adjacent over hypotenuse, so negative 1 over root 5. Or if we want to rationalize, this would be negative root 5 over 5. Just multiplying the top and bottom by the square root of 5. I should mention we could also get these values of cosine for alpha and beta using the identity sine squared plus cosine squared equals 1. So in this case, since we know sine, we can say sine squared, so negative 2 over root 5 squared plus cosine squared equals 1. And then solve for cosine. So if you do that, you should end up with the same result. We'll still get a plus or minus when you take the square root of both sides, so we still need to continue or consider which quadrant we're in to decide if the cosine will be positive or negative. And here, since we're in the third quadrant, cosine should definitely be negative. So just want to add that alternative way that we can get this. You wouldn't have to build a triangle, but ultimately we are doing the same thing, just in a slightly different form. All right, let's continue. We have now, notice now we know sine of alpha and cosine of alpha. We know sine of beta and cosine of beta. So we can answer any angle addition or subtraction formula involving alpha plus beta or alpha minus beta. So part C asks for cosine of alpha plus beta. So let's remember the formula was for the cosine just gets double cosine and double sine, and then the sign will flip and become a minus. So just to remember, it's cosine of the first angle, so cosine alpha, times cosine of the second angle, minus sine of the first angle times sine of the second angle. And we know all these individual pieces now, so let's just plug it in. The cosine of alpha we said was negative 3 over 5. So I'll fill these in first and then I'll scroll down. The cosine of beta we just found was negative root 5 over 5. The sine of alpha was 4 over 5. And the sine of beta was Let's use the rationalized version, negative 2 root 5 over 5. So that's coming from this given information from the question prompt. All right, and then scroll down. So we got it plugged in. Let's just evaluate and simplify. So the first two terms, we have two negatives, so it'll become positive. So this will become positive 3 times root 5 over 25. Then, since we have a minus here, but then also this other negative, that should turn this into a positive as well. So this will become plus. The 4 will multiply with the 2, so that will become 8 root 5 over 25. So now these can combine like terms because they both have a root 5. So 3 root 5 plus 8 root 5 will be 11 root 5, 3 plus 8, over 25. And we can stop there. And then part D was asking for the sine of alpha plus beta. Oops. Alpha plus beta inside of the sine. So with the sine, the sines and cosines are mixed together. So we get the sine of the first angle times the cosine of the second angle plus, because sine follows that sine, plus the cosine of the first angle times the cosine of the second angle. So let's plug everything in. The sine of alpha was 4 over 5. The cosine of beta was negative root 5 over 5. Plus the cosine of alpha, which is negative 3/5, times the cosine of beta. Oops, nope, wrote this wrong. This should be sine here. Yeah, sine, cosine, cosine, sine. Sorry about that. So cosine of alpha was negative 3 over 5, and the sine of beta is our negative 2 root 5 over 5. All right, just double checking everything. Sine alpha, cosine beta. Cosine alpha, sine beta. Okay, everything looks good. So this will become negative 4 root 5 over 25 plus, and it'll stay positive because we have negative 3 times negative 2, so plus 6 root 5 over 25. So negative 4 plus 6 will give us positive 2, so 2 root 5 over 25. Yeah, for the sine, sine, cosine, cosine, sine, and then it's first angle and second angle. All right, so let us practice using these identities in order to establish some other identities. So let's take a look at what they're giving us here. It says establish the identity cosine alpha minus beta over sine alpha sine beta. We're saying that this should be equal to the cotangent of alpha times the cotangent of beta plus 1. So let's see how we can get there. Well, let's start by just expanding things out because we don't end up with any angles that look like alpha minus beta. So let's use our new identities to expand out the numerator. cosine of alpha minus beta will be cosine of alpha cosine of beta plus the sine of alpha times the sine of beta. Cosine angle subtraction, cosine, cosine, sine, sine, and it's a minus which becomes a plus in between. That's how I recall. And our denominator will keep the same. So over sine alpha, sine beta. So what should we do now? Well, we can always try splitting this into two separate fractions. Like what we have is basically something plus something over a common denominator, which you can always split up into, in this case, like a over c plus b over c. It's like going backwards. A lot of times we're at this point and we combine something together into a single fraction with the common denominator. Well, we can go in the opposite direction too. We can split things apart. So let's do that. Let's take that left part, which is cosine alpha, cosine beta, and it will be over the denominator, sine alpha, sine beta, plus the right part of that numerator, sine alpha, sine beta, over the same denominator, sine alpha, sine beta. And notice those are the same, so everything will cancel for that second fraction. We'll be left with just a positive 1. And on the first fraction, notice we have cosine alpha over sine alpha. That's the cotangent of alpha. And then cosine beta over sine beta. That's the cotangent of beta. So this will give us our right-hand side of that original expression. So cotangent alpha times cotangent beta plus 1. And that was our right-hand side. So we can use this in the middle of an identity as well, or in order to verify some other identities. We also have similar sum and difference formulas for the tangent. So let's see how we can derive some of these. They just show us the formula here. Tangent alpha plus beta is tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. How can we get that? Let's remember that tangent is sine over cosine. So really we can express this as the sine of alpha plus beta over the cosine of alpha plus beta. So let's expand both the numerator and the denominator. So sine of alpha plus beta is the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. And the denominator, cosine of alpha plus beta, will be cosine alpha cosine beta minus sine alpha sine beta. So what can we do from here? Well, let's keep in mind that we want to produce some tangents. So for a tangent, we need sine over cosine. So, and we also want a 1 in that denominator. Basically, we want a 1 in this position in the denominator. So the trick here is to multiply the numerator and denominator by 1 over cosine alpha cosine beta. So we'll do that on the top and bottom. It's going to create a bunch of fractions, and we'll see how things simplify from there. So let's just be careful. So in our numerator, this term is going to distribute to both of these and create a fraction where what we already have will be the numerator, and then we'll have a cosine alpha cosine beta in the denominator. So that first term in the numerator will be sine alpha, oops, let me make this smaller, sine alpha cosine beta over cosine alpha cosine beta. So over this denominator, plus our second term in the numerator was cosine alpha sine beta. This will also now be over cosine alpha cosine beta. So that's just our numerator. Our denominator, the first term will have the cosine of alpha cosine beta. Now over also cosine alpha cosine beta plus, or no, I'm sorry, minus, so looking at that denominator up here, minus sine alpha sine beta this also gets divided by cosine alpha cosine beta. So let's see what cancels. In the numerator, on the first term, we have cosine beta on the top and bottom, so that will cancel. In the second term, we have cosine alpha on the top and bottom, so that will cancel. In the denominator, that first term will completely cancel into 1. Oops. Because we have cosine alpha cosine beta over cosine alpha cosine beta, so that'll become 1. And then the second term, nothing will cancel, but we can see we'll get some tangents out of everything that remains. So up here, sine alpha over cosine alpha gives us the tangent of alpha. Our second term, sine beta over cosine beta, will give us the tangent of beta. Then on the denominator, the first term reduces to 1. We have a minus, and then that second term, we have sine alpha over cosine alpha, so that's tangent alpha. And we also have sine beta, should have been a beta here, sine beta over cosine beta, so that will give us a tangent of beta. Which is our first identity, the tangent of alpha plus beta. So you don't have to have this whole process memorized. We're really just showing where this identity is coming from. Now that we have the angle addition and subtraction for the sine and cosine, we can divide them and get tangent, and probably something similar for cotangent. And we can produce our second identity for angle subtraction just using a subtraction of these angles. Everything else will be pretty similar. So again, you don't have to have this whole process memorized. You can just reference these identities. Just wanted to show where it's coming from, how we can rederive them. So in general, tangent angle addition, alpha plus beta. In the numerator, you get the sum of the tangents of the separate angles, tangent alpha plus tangent beta. In the denominator, 1 minus tangent alpha times tangent beta. And notice for angle subtraction, it looks the same, but the pluses and minuses are swapped. So you have a subtraction in the numerator and an addition in the denominator. So let's practice using these in a few examples. So it's having us establish a few identities here. It's saying, establish this identity that the tangent of theta plus pi is just equal to the tangent. Well, let's use our angle addition identity for the tangent. This should be the tangent of the first angle, which is just theta, plus the tangent of the second angle, which is pi, divided by 1 minus the tangent of the first angle times the tangent of the second angle. And so what is the tangent of pi? Well, tangent of pi is the sine of pi over the cosine of pi. Sine of pi, thinking about being over here on the unit circle, that's the coordinate point -1, 0. Sine of pi is 0, cosine of pi is -1. That would just reduce to 0. So notice this will give us tangent of theta plus 0 over 1 minus the tangent of theta times 0, because we get another tangent of pi here. So this all reduces to just tangent in the numerator and just 1 in the denominator, because that will become 1 minus 0. So just the tangent. So it's saying if we have the tangent of some angle, and then we look at the tangent of 180 degrees more than that angle, we get the same value. This is another way of observing the periodic nature of the tangent. Remember we said that the tangent had a period of pi. So it makes sense that if you add pi, you're just skipping to the next period and you get the same tangent value. So another approach of seeing the periodic nature of the tangent, but without looking at the graph, now just using this analytic approach of working with the identity. So let's do the same thing for example 8. We want to establish that the tangent of theta plus pi over 2 equals negative cotangent of theta. So let's see, how can we get there? Well, we can do a similar thing, except we would end up with tangents of pi over 2. And let's remember that the tangent of pi over 2 is actually undefined. This is the point 0, 1. Sine over cosine would be 1 divided by 0. So tangent of pi over 2 is definitely not defined, but let's try expressing this in terms of sine and cosine. We can say this should be the sine of theta plus pi over 2 divided by the cosine of theta plus pi over 2. Let's expand that out. For sine angle addition will be sine of the first angle, which is just theta, times the sine of the second angle. Or no, I keep getting these mixed up. For the sine, it's sine, cosine, cosine, sine. So sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. So that will be our numerator. And then for the denominator, cosine of theta plus pi over 2, that one has the cosines and sines paired together. So cosine of the first angle, which is just theta, times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. So let's evaluate what we can. We have the sine of theta. Anything with theta will just have to stay there because we're not evaluating it as anything. So sine of the first angle, cosine of pi over 2 is 0. So this will be times 0 plus the cosine of theta times the sine of pi over 2. Sine of pi over 2 is positive 1. And this is over the cosine of theta times the cosine of pi over 2. That will again be 0. Minus the sine of theta times, again, the sine of pi over 2, which is still positive 1. So this becomes, the first term will be 0, so 0 plus cosine. We get positive cosine in the numerator. And then on the bottom, we'll have 0 minus sine. So cosine over negative sine of theta, which cosine over sine is cotangent, and we have that negative, so negative cotangent. So just using these identities in order to verify or establish other identities. And this one was tricky because of this pi over 2. In the last example, we were able to directly use the angle addition for the tangent, but we would end up with some undefined values here for the pi over 2 angle. So we could also take the sine over cosine approach and apply their separate identities and then reduce the result. All right, our next section throws in some inverse trig functions inside of our angle addition formula. So let's take a look. They're giving us the sine of the inverse cosine of 1/2 plus the inverse sine of 3/5. Well, the output of inverse trig functions are angles, so we can call that inverse cosine of 1/2 alpha, and the inverse sine of 3/5, let's call that beta. So let's try to work through this. This will be a good starting point. We can say the inverse cosine of 1/2 is equal to some angle alpha, because we want to expand this into, since it's the sine, it'll be sine of alpha cosine beta plus cosine alpha sine beta. So if we can get some expression for each of these, we'll be able to plug it in and evaluate. So the inverse cosine of 1/2 equals alpha. We can take the cosine of both sides and say that alpha equals the cosine of, or I'm sorry, it would be 1/2 is equal to the cosine of alpha. So where's the cosine equal to 1/2? And let's keep in mind our restricted range of the inverse cosine is from 0 to pi. And it's positive, so we're in the first quadrant. So that should be at pi over 3. We get a cosine of positive 1/2. So we can say alpha equals pi over 3. And I'm doing this because we want to try to find out also what the sine of alpha is, because we have the cosine alpha, but we also have the sine of alpha. So we need both the sine and cosine. So if our angle is pi over 3, then what should the sine be? Well, pi over 3 has the coordinate point 1/2 root 3 over 2. So that means the sine should be root 3 over 2. Sine of alpha is root 3 over 2. Cosine of alpha is 1/2. Our second statement says the inverse sine of 3/5. Let's call that beta. So we can take the sine of both sides. We get that the sine of beta equals 3/5. Here we'll need to build a triangle. It'll be in the first quadrant since sine is positive. And the inverse sign is bound between negative pi over 2 and pi over 2, so it should be up there in the first quadrant. And sine is opposite over hypotenuse, so this would be a 3 and a 5. Call this beta. And there's our 3 and 5, so this must be a 4. It's a 3, 4, 5 triangle. But we can get that also from Pythagorean theorem. So from here, we already know that the sine of beta is 3/5. So we can use the triangle to get the cosine, which is adjacent over hypotenuse, so 4/5. Now we have everything that we can plug in. Because this is really just sine of alpha plus beta, which we've expanded out here. So let's plug in all of the values that we know. Sine of alpha is √3 over 2. Cosine beta is 4/5. Plus cosine of alpha is 1/2. Sine of beta is 3/5. So this will become 4√3 over 10 plus 3 over 10. So we can combine that into a single fraction, 4√3 plus 3 over 10. And I bet the text probably pulls out the 1 over 10 with 4√3 plus 3 inside. That's kind of their aesthetic, what they like to express things as. So I'll leave it like that. But if you said the previous step, it's still equivalent as well. All right, let's look at another example in the same kind of style, where things are more abstract. It wants us to write this expression, the sine of the inverse sine of u plus the inverse cosine of u, as an algebraic expression containing u and v, meaning without trigonometric function. Well, let's take a similar approach. Let's just call what is inside, let's call that alpha, and let's call this part beta. So I will say, and ultimately we want to find out what is the sine of alpha and the sine of beta and the cosine of alpha and the cosine of beta. We need those 4 pieces so that we can use the angle addition formula for the sine. So we can start off by saying the inverse sine of u equals alpha. And I'll just make a note that alpha needs to be between negative pi over 2 and pi over 2. That's the restricted range of the inverse sine. So I'm doing this because they say also state the restrictions on u and v. All right, so we can take the sine of both sides and get a statement that u equals the sine of alpha. So from here, if you remember when we did this in a previous video, we can just build a triangle using this statement. You can see that as u over 1. So imagine some triangle. We'll call this angle alpha. Sine is opposite over hypotenuse, so this will be u. Hypotenuse will be 1. And let's solve for this unknown side. I'll call it x. You can say x squared plus u squared should equal 1. So using the Pythagorean theorem on this triangle. Then we just need to subtract the u squared over. So x squared will equal 1 minus u squared. Then take the square root of both sides. Technically we get plus or minus 1 minus u squared, but this should be a positive side length here, since we are in the either the first or the fourth quadrant. The cosine value will be positive, or the x distance will be positive. So then let's list out our sine and cosine. We can say the sine of alpha equals u, and the cosine of alpha is adjacent over hypotenuse. It'll just be the square root of 1 minus u squared over 1 technically. So that's our first piece that we need. Now let's do the same thing for v. We can say the inverse cosine of v equals beta. We know beta needs to be in between 0 and pi. That's the restricted output of the inverse cosine. So we can take the cosine of both sides and say v is equal to the cosine of beta. So we can build another triangle. Let's call that beta. And we can view this as a v over 1. So cosine is adjacent over hypotenuse, so this will be a side length v. This will be a 1. And kind of citing this work from our last triangle, if we did the Pythagorean theorem, we should get the square root of 1 minus v squared here. Because like we had u and 1, and that other side length was the square root of 1 minus u squared. So you'd get a similar result. So let's use this to list out the sine and cosine of beta. Sine of beta is opposite over hypotenuse, so the square root of 1 minus v squared over 1. Cosine of beta is adjacent over hypotenuse, just v over 1. So now we have all our pieces. Let's just plug in to our formula. So what we have, or what we're looking for, is the sine of alpha plus beta. So that should be sine alpha cosine beta plus cosine alpha sine beta. Here, let me write this. I'll just write it below because I kind of ran out of room here. So sine alpha cosine beta plus cosine alpha sine beta. Sine of alpha is u, cosine beta is v, plus the cosine of alpha is the square root of 1 minus u squared, and the sine of beta is the square root of 1 minus v squared. And the text leaves it like that. We could technically multiply these square roots by each other and get a single square root, but they probably think it's nicer. It'll become more complex inside a single square root, so we can stop here. Alright, so that was more abstract. In practice, like in our homework questions, we'll be dealing more, you might see one like this, but it will be more like what we've seen previously, where we need to use the sum and difference formulas and evaluate them at some unit circle angles. So like these examples. Alright, let's see one more where we need to solve a trigonometric equation. They're saying that's linear in sine and cosine. So there's a little trick that we can use here. Alright, so we have the sine of theta plus the cosine of theta equals 1. And we want all solutions that are in between 0 and 2 pi. So what can we do here? It's hard to see which identities we should use. One trick that we can do is to square both sides of this equation. So let's square the left side, sine of theta plus cosine theta. Let's square that side, and we can also square the right side. So what will we get when we square the left side if we FOIL that out? So we're doing essentially sine of theta plus cosine of theta squared. Like we have this times itself. Might be better to write this out. So multiplying our two first terms, sine times sine, will give us sine squared. Then we'll get plus sine cosine, then plus another sine cosine. So we'll get two of those. So I can say plus 2 sine theta cosine theta. Then our last two terms will be cosine times cosine. So plus cosine squared. And this is equal to 1. So what can we do from here? Notice we have sine squared plus cosine squared. So we can use the Pythagorean identity that should be equal to positive 1. Sine squared plus cosine squared equals 1. That's our classic Pythagorean trigonometric identity. So those two terms will become 1. We still have the 2 sine theta cosine theta. And this is equal to 1. So now if we subtract 1 from both sides, we get 2 sine theta cosine theta equals 0, and then divide both sides by 2, we get the sine of theta times the cosine of theta just equals 0. 0 divided by 2 is still 0. So now we have two things multiplied equal to 0. We can apply the 0 product property and just take our first term, the sine of theta, that'll be equal to 0, and then our second term, the cosine of theta, will also be equal to 0. And let's solve these separately. Where is this true from 0 to 2 pi? The sine of theta is 0. Well, that happens at 0 and pi. So I can get two solutions. And then the cosine is equal to 0 at pi over 2 and 3 pi over 2. So I have to be a little bit cautious here due to when we squared both sides of the equation earlier, that might produce some erroneous results. So we need to check each of these solutions. I'll check it back in the first equation, sine plus cosine equals 1. We'll plug these in and see if they make sense. So let's check our first angle of 0. This would be the sine of 0 plus the cosine of 0. That will be 0 plus 1, which is positive 1, so that one works out. For pi, we have the sine of pi plus the cosine of pi. Notice this would give us 0 minus 1, because cosine of pi is negative 1, which is negative 1, not equal to this 1 that we want, so we have to throw out that result. It can't be pi. Let's try pi over 2. Sine of pi over 2 plus cosine pi over 2. That is 1 plus 0, so positive 1. That one works out. And for 3 pi over 2, you can already maybe see what's going to happen. Sine of 3 pi over 2 plus the cosine of 3 pi over 2. This is negative 1 plus 0, which is negative 1, so we can't have that result either. So we got to throw out 2 of our solutions here. So we can just say that theta will equal 0 or pi over 2. So if you have to square both sides of an equation in general, and this also applies now with trigonometric equations, you'll need to check your results, because we only want this to be equal to positive 1. So we might get some erroneous results here. Alright, that one was a little bit different from our previous examples. Again, the main thing I want to get out of this section is working with these formulas. So angle addition for sine and cosine. For cosine, it's like cosine A, cosine B, plus or minus sine A, sine B. The sines and cosines are paired together. For sine, we have sine A, cosine B, plus or minus cosine A, sine B. And for the sine, if it's a plus in the formula, you see a plus in the right side as well. And then for tangent, you get tangent A plus tangent B over 1 minus tangent A times tangent B. That's if we have a plus here. If it's a minus, we get the same result, just with a minus on top and a plus on the bottom. So if a lot of times you'll be given formula sheets, especially as we add more and more of these identities. But you can pick up on little patterns like this if you are in a situation where you have to memorize some of these. Unlike, say, like for the tangent, you see the same plus sign or minus sign on the numerator, and the denominator flips it from either a plus to a minus or a minus to a plus. Because a lot of these start to look very similar to each other, so you can try to develop little tricks to build them into memory. Alright, that's it for this section. So we used the sum and difference formulas to find exact values. We also used them to establish a couple identities. We did a couple questions involving inverse trig functions. And then that last one was solving a trig equation that's linear in sine and cosine. That's it for this video, and I'll see you next time.